Welcome everybody to this session. I'm very happy to be presenting this jointly with Stephen, Jonathan, and Benjamin. My name is Paul Goosens. I am going to effectively be the master of ceremonies for this session. I'm going to start the ball rolling just to talk about some of the business motivations behind some of the work that we have done with Bloomy in terms of integrating our battery models into the BMS test platform. Might be then introducing Stephen to take you into some of the detail of that platform. Then Jonathan will spend a bit of time going into some detail on some of the sort of unique aspects of the MapleSim battery library, which has kind of driven people to use our models. During that time, after that, we'll talk about the integration of the models together, and we'll have a short demonstration to give you a sense of what the workflow is like within this environment. Hoping that this whole session will take about 50 minutes. We'll have about 10 minutes left for questions after that. So let me make a start. And as I say, we've had a number of customers have come to us over the years, really struggling with what they see as a disparity between the results that have come out of hardware-in-the-loop tests and actually with the real-world experience. And some of this can be quite detailed things like being able to handle charge recovery, charge imbalance, thermal losses, and of course degradation over the life of the battery, and a lot of certainly a lot of equivalent circuit types of models that are typically used in this scenario really fall short in terms of being able to deliver that kind of level of fidelity. What does that mean in terms of the business of testing BMSs? Well, part of it can you end up with the risk of actually under-engineering. You test for certain load conditions you think are what the battery and the BMS system are going to actually experience in the real vehicle. But of course, then there are a lot of unforeseen load conditions that can produce accelerated aging. Certainly, we've seen instances where those unforeseen load conditions have resulted in thermal runaway, and fundamentally, we've seen some very high-profile product recalls in this particular area. Of course, the flip side to all of this is that in order to try and address those risks in terms of the unforeseen, there is a tendency towards over-engineering, which of course then adds cost and weight to the final product, which may be unnecessary. So given that, there is a drive for greater model fidelity, and that's really where we, Maplesoft, come in terms of our physics-based modeling capability, in terms of how this would work within the BMS system that Bloomy offer, is that we can actually integrate our battery library models either as a cell or a stack or a complete battery into the LabVIEW Veristand environment within the Bloomy system platform, and these are the kinds of things that we're able to offer: rigorous electrochemical physics-based models that have the kind of details that help in order to make the BMS tests much more realistic. I'm not going to go into any detail. I'll be passing over to Jonathan to talk about this. This is just a summary of the kinds of things that certain artifacts that our battery library can offer, and Jonathan will talk in a lot more detail on that. So at a very high level, that's what's driving both Maplesoft and Bloomy together in order to produce this system. With that, I'll pass the microphone over to Stephen to give you his description of the BMS system. Over to you, Stephen.
Very much, Paul. Pleasure to be here, and thank you to everyone at Maplesoft for allowing this to happen. I will first share my screen. Excellent. So closer to reality, the Bloomy BMS HIL Test platform that you see there on the right really represents our taking those physics models, the models that are being produced by Maplesoft, and really taking them and bringing them to reality so you can actually test your physical hardware. So the BMS itself, just to take a step back, what is it? It's really found in many intelligent battery applications, from small products like cell phones and power tools all the way up to large-scale grid storage systems. And the primary purpose with advanced lithium batteries is to manage and control those battery cells, really to maximize the power of the battery, to improve its life, to control the charge and discharge functionality of that battery pack, to ensure safety and auxiliary I/O, to make sure that the product actually operates in a safe and usable state, and finally external communication so that it can be a subsystem within a greater system, such as an automobile or an aircraft. Why do we need it? As you may be aware, if you're in the industry, in the battery industry, each cell of the battery, of a lithium battery, has to be monitored and balanced in order to optimize its performance. We need to ensure safety so that we prevent overvoltage limits, thermal runaway, basically situations beyond the bounds of the actual system operation. Extending the battery life through optimal performance and capacity, addressing things like capacity fading, making sure that doesn't happen, and communication. We want to essentially optimize how this battery performs from a safety and a performance perspective. So just to go over some of the basic primary functions, we have this sheet right here that actually demonstrates in this chart. And you have things from cell protection, cell balancing, state of health, charge and discharge control, monitoring, and contactor control. Basically, all these features of the BMS that need to operate, we want to make sure that we are able to test them and prove that they're performing correctly and prove that in real time. So that if you have a safety feature, you want to make sure that it responds in a timely and effective manner. So part of the BMS test, of testing a BMS, is to effectively test each feature that the BMS provides. So what is hardware-in-the-loop testing? It's essentially a technique for developing and testing complex real-time embedded systems, of which the BMS is the case. And we're using mathematical models, physics models, essentially models to replicate what the actual product itself is doing. So instead of using an actual battery cell to simulate the pack, to operate the pack and test the BMS, we're actually using a simulation, and it allows us to do the testing much more effectively and reliably. So you have your embedded system, your BMS that you can see up here on the right, and we're going to use a HIL simulator, or in some cases a simulation of the battery pack. In other cases, we're going to simulate the vehicle itself and really use this model to output sensor signals, input control signals, and really make sure that the embedded system itself, the battery BMS, thinks it's, for all intents and purposes, connected up to an actual battery pack or electric vehicle. And the idea there is to model every single signal that the BMS expects and make sure that we rigorously test its functionality. So the approach that Bloomy provides is really an open system approach, and this is how it plays very nicely into the physics models that Maplesoft is providing. Our solutions, which I'll demonstrate in a few moments, uses commercial off-the-shelf COTS hardware and software components conforming to an open published standard. We build the platform allowing a user-defined system. So our system isn't a closed system that conforms to what we want it to do. It's basically an open platform that conforms to what you, the user, would like to see in your system. So this allows for modular mix-and-match components from multiple vendors. It's well documented and supported and scales to meet the user and the product need. So you see all these components on the right. You see the National Instruments PXI chassis, single board Rio, SOMS, you see compact RIO, vision systems. That's on the hardware side. On the software side, there's different software platforms that support these as well. And then on the bottom, you have the products from Bloomy that are COTS components as well. Each of these slip into the system. So the open system approach really facilitates best this scalability and usability in a way that supports the rapid evolution of the EV market. Things are changing very quickly within the market. Requirements of system performance is rapidly changing. So really the need of the market has been to have test equipment that can support that rapid evolution as well. And that's how the open system approach really matches. So really just going through some of the challenges that we implement. The first is getting rid of the battery. We don't want to use a battery when we're testing a BMS. It introduces numerous concerns, cumbersome resources for charging and discharging the battery. There are safety concerns. Operating a cell at a over voltage or over over temperature situation can create very serious safety hazards. And we really don't want to be, essentially when we're testing a BMS and its ability to prevent these situations, we don't want to get the product into that state to begin with. Using a battery presents consistency challenges in terms of getting to the same states of charge and states of health situations or states on a consistent basis. And from a throughput standpoint, if I need to charge and discharge my cells every time I want to test different states or simulate real-time situations, it's going to be a very slow throughput. And the logistics of managing a factory full of batteries can be quite a challenge as well. So that introduces cell simulation, which is really at the core of what we're presenting today, simulating the cells themselves that are part of the pack, and simulating them through the Maplesoft models. And using cell simulation allows us several key features. Instantaneously achieving states. You can simulate and get to the point of state of charge that you want to very quickly and very accurately. You can safely operate at high voltages, not having to actually use power-generating cells as part of your BMS testing. Non-destructive testing, a Bloomy fault insertion unit, which you see down here on the bottom right, allows you to create open circuit or short-to-rail type faults without actually damaging the cells or creating a potential for damaging your test equipment. No need anymore for stock maintenance. And finally, a commercial, off-the-shelf, scalable, flexible product that can be scaled, inserted, and managed within your test system. So the battery simulator that Bloomy provides can simulate different cell configurations and pack voltages. The pack voltages scale based on how many of these cells you use and how many you configure in a series formation. And the cell configurations are really very dependent on the models that you're going to be using from the Maplesoft library. So in essence, you have the ability to create varying size and style of a cell that's used for the BMS test. In terms of simulating the rest of the BMS Signal I, we use PXI and compact RIO to simulate all the other signals that are coming out of the BMS from a control standpoint. This can be RTDs and thermistors, fault and control I/O, PWMs for pump drive and things of that nature, ECU interfaces, and pack voltage and current sensors in terms of the signals that the BMS is monitoring. We also use power supplies for pack current and pack voltage simulation, as well as power management. So essentially every signal that your BMS is expecting to see is coming from some variation of a PXI compact RIO or commercial off-the-shelf power supply product, as well as from a battery simulator or fault insertion unit. We then have that same approach with software execution. We use Veristand for hardware-in-the-loop software. So that allows us to interface with models that are provided by Maplesoft or any other modeling resource. It also interfaces with the hardware I/O. So Veristand interfaces to the battery simulator, PXI, and any other commercial off-the-shelf equipment. And it allows us to apply drive profiles. What happens to your model as you run through a charge or a discharge or some other type of performance profile. We use TestStand to create test execution capabilities to run through tests in a repeatable and consistent fashion, and use LabVIEW for custom signals such as PWM and custom I/O, as well as custom GUIs if you need an interface that specifically meets your test need. So putting these all together, you see the image, what Paul had shown before. And what you see here are two boxes. One on the left shows the actual HIL system. The one on the right shows the battery management system. And you can see here that there's very distinct components. The battery simulators in green, which can be scaled up and down up to 200 cells or 1,000 volts. Your control signals, analog, digital I/Os, thermistors, current transducers, and fault induction. All these signals can be output to your BMS, as well as communication and any other auxiliary measurements. And on the right, you see that this is the BMS and the I/O interface components as well. And the open aspect of this is that any one of these components can be replaced, scaled, and varied based on the specific needs of your BMS. So a common method that this BMS platform allows is a quick interconnect change to allow you to connect to different BMSs by using different interconnect cables to go to your BMS, along with a little bit of configuration of your I/O. Here you see the real-time controller that runs National Instruments Veristand, and this all happens on PXI as well. And this is where we tap into the cell models. So all these cell models connect up to your simulators, your control signals, communication, and auxiliary measurement. And these signals, these cell models, are really the heart of how this HIL system operates. Within that component, we can run cell models, stack models from really any source of modeling input. This could be done in LabVIEW if you want to stay within the National Instruments environment, or easily switch to a higher-end modeling resource such as Maplesoft. And this is really how we create an open concept that takes the models and puts them actually into reality. We're taking models that operate how the cells should be operating in physics theory, and then really take those signals, both from an input and output standpoint, and really translate them into the physical signals that your BMS is expecting. So in essence here, turning that into reality. So with that, I will turn it over to Jonathan and let him continue with the actual battery library details.
Thank you, Stephen. All right, so Stephen's done a really good job explaining the context in which the model environment can add into the hardware. So now I get the opportunity to explain a little bit more on the modeling side. So to give a bit of context on where MapleSim is in the modeling space, I'm going to show a little bit of a preview of the software tool itself. So that's what we can see on the screen. On the left-hand side, we have a whole host of library components available to you. Specifically, we're looking at batteries today. So, of course, we have our electrochemical batteries and equivalent circuit batteries shown here, along with many other libraries that are available. And these allow for components that can be easily dragged and dropped into your workspace, which is in the center. And you can create the desired architect that you're interested in modeling. When you want to modify or change any of the aspect of your modeling environment, you simply click on any of the components you're using, and you can change the parameter settings as we see on the right-hand side, for instance, whether we're changing the chemistry or some of the desired parameters for our individual cells. We'll extend on this concept a little bit as we get into this a bit more. So there are two approaches that are developed in our library. Of course, the equivalent circuit battery model. This is excellent for representing the circuit in a fairly well-understood process using electrical components. It's fairly easy to understand and has a fairly limited number of parameter sets. However, when we want to look at a wider range of applications where we're applying different current, it's very useful to use the electrochemical model, where we bring a lot more physics and understanding of what the actual cell is doing into our modeling approach. This results in significantly more complex equations and a larger parameter set to deal with, and we have ways of handling that. So a little bit about our electrochemical model. Well, the chemistry-based model is using the first principles of electrochemical modeling. This is extending the concept of the dual foil model developed by John Newman and colleagues, where we're taking a look at the 1D transfer of lithium ions to the porous electrode and porous separator. This results in 10 PDE equations defining the mass transport, diffusion process, electric potential balance, as well as our two Butler-Vollmer equations. How we approach our PDEs is a little bit different than many classical approaches, which tend to be fairly computationally expensive. We actually use a method called the Galerkin method. This gives us the advantage of being able to calculate these PDEs in much faster, and actually enables our electrochemical modeling to be used in real-time applications like the HIL environment that was introduced earlier. So some example of some of the equations. Here we see the solid phase and liquid phase mass transport equations. So the solid phase and liquid phase, defining the lithium ion concentration as it moves throughout the cell. There's a lot more content on the equation definitions on some of our other additional literature material, but to give a sense of the equation structure that we are using, as well as the fact that we use Ohm's law and Kirchhoff's law within the cell, and Butler-Vollmer equations are included in this structure. We approach the open circuit voltage using the two half-cell methods for bringing in the charge response as a function of state of charge. So here we even see an example of our two cathode and anode materials, where we can see the potential difference as the function of state of charge for the half cell on the cathode and for the anode, and the equation that defines this relationship for the potential on the positive side and the negative side. The open circuit voltage is also affected by thermal properties, so we made sure to include our thermal characteristics. So whether it's the loss power that you'll use as the applied current is lost through the heat inside the cell and that's not recoverable, or the cooling system that's added to the cell itself, we have that modeled, as well as the enthalpy change effect that is going to be changing the behavior of whether the cell is heating up due to charge or discharge, and the contribution from the two half-cell circuits. The enthalpy reaction then as a result can be defined for each of the chemistries we're using, like the equations we see here in the middle. And the temperature can directly then affect our open circuit potential on each of our cells. As the cell heats up, we treat the cell as one lump mass, and we're able to store that temperature change as the cell capacity is able to take a certain amount of temperature and will continue to rise. And we'll be able to also look at cases where whether we have good thermal management or do we need to add additional considerations for those in our models. We can easily do that by looking at our MapleSim environment again, where we can drag our model of our battery into the environment, connect it to any of the circuit components that are outside of the battery cell that we're interested in, and start bringing in some of our thermal library characteristics like we see here, where we can have our air cooling to some kind of external air supply, or even if we have connections to other areas like liquid cooling. So we can bring in our library components and then adjust them and select the anode and cathode material. We have 14 cathode material items to select from, as well as 4 anode materials available to you out of the box. If, however, you are interested in defining your own material, that is also available. We can simply select user-defined, and you can specify the half-cell characteristics for the enthalpy change, as well as your open circuit characteristics. Now, if we take a look at some of the simulation dynamics that we're interested in, here on the left-hand side, we can see a discharge voltage response with the pulse current applied. You can see that the overall trend results in a very typical discharge characteristics, as well as as well as our short-term and short-term discharge, where we can see that there's a transient period and a recovery period as the pulse is relieved. When we take a look at the voltage response, we can also compare different materials, such as our different cathode materials, and apply the same current for discharging our cell, and we can compare and see which cell is best suitable for our application. The same type of study can be extended for any thermal consideration that we might be interested in. On the left-hand side, we have a couple of cases showing different thermal management with a 30 ampere hour lithium-ion cell being discharged at 10 amps, all the way from an extreme adiabatic solution where we have no cooling available to the cell. We can see significant temperature increase over time, to significant cooling available where there's marginal temperature change, and being able to select any point in between. Other considerations, of course, relate to current variation over time, and given a constant heat transfer that the cell might be able have available to it. And we can see a very nonlinear effect in our temperature change. When we take a look at a lot of our experimental results, it's very useful to be able to adjust and modify our cell data to match the experimental characteristics that we're actually interested in for your individual data. As a result, we've also included a parameter fitting tool as part of our library, and we've even broken it down into different regions, whether there's the basic parameters that encompass the majority of the tuning that most users will be interested in, as well as having advanced and thermal parameters that can be easily identified and help you with identifying the characteristics for your cell. We can see on the right-hand side the experimental results in the solid lines for 2 different discharge curves, as well as the dotted lines, the fitted response from our parameter fitting tool. When we move into battery management systems, it's very important to include degradation effects or state of health characteristics. We've approached this by looking at the solid electrolyte interface. As the SEI film builds up on the anode during charging, we can see that the film results in increased resistance and can negatively impact the cells. To better illustrate this, if we take a look at some of your experimental as well as simulated results, we can see two different battery cells being used, one operating at 15 degrees Celsius and the other one at 60 degrees Celsius, for the cell being discharged and recharged over a large number of cycles. You can see on the bottom here the cycle count as well as the state of health, where one being a perfectly healthy cell, and as we decrease in our state of health quality, we continue on until perhaps we get down to 0 as the cell is completely depleted. In most cases, the cell is damaged or beyond functional use well before then. It's important to note that state of health is a function of temperature, applied current, depth of discharge, and cycle time. And all these considerations are already added into the state of health modeling. When we put some of these concepts together as part of some approaches that are required for the battery management system, we can also expand the thermal management to include characteristics such as the container that the cell is sitting in, some cooling that might be available to the container with perhaps passive airflow over it, as well as any other chambers that the container might be encased in. When we start applying current at different loads, we can see the temperature response for both the cell and the container itself. And when we significantly ramp up the current going through the cell, we can see that the cell itself rockets up past any of our warning limits, and in fact, in this case, even exceeds our danger point, resulting in termination of the simulation. We can see even that the container itself has gotten significantly hotter and can indicate key aspects that the battery management tool can use to help manage the thermal properties of the pack, the cell, or any of the stack components. Finally, I'd like to go and show a case study where we worked with one of our customers in the past. In this case, we were able to use a 144 cell that was designed for their hardware-in-the-loop testing. They were interested in having individual cell balancing current, as well as being able to read out their individual state of health, state of charge, and voltage for the cells. From the experimental results, each one of their cells had a slight difference in the voltage response. Approximately a 14 millivolts discrepancy at the sampled point as the voltage of the cell changes as a function of time when the cells are being depleted. In simulation, of course, we want to make sure that we can replicate that type of dynamics, and using a statistical approach, we're able to change some of the cell properties that have been identified and vary them slightly to allow for that range of operation. And as a result, in our simulated results, we can see a 13 millivolt approximate fit to give the same kind of characteristics we saw in our experimental results, also available in our simulated results. At this point, we can package up the entire cell, stack, or battery pack put that into a functional mock-up unit, effectively a module that we can then pass on to any of the software that we'll be running in our hardware system, and have that run on our real-time platform. So I'll be handing this off to Ben to explain a little bit more of that approach in his demonstration.
Hi, so Stephen spoke earlier about the BMS HIL rig, and Jonathan just spoke about the MapleSim models. What I'm going to talk about is basically how these two come together. This demo is basically supposed to represent exactly what a HIL rig, the software in a HIL rig would be doing during a test. So Jonathan just spoke about the models. So what we do is import these models into NI Veristand, which is a software environment that's basically intended to configure real-time test applications. You can see right here the models you can command, status, model time, and you can, Jonathan just spoke about the imports and outports of these models. So in this case, we're looking at ambient temperature, the balancing current for each cell, the pack current, and from there we can get the individual cell state of charge, individual cell temperatures, individual cell voltage, the pack temperature, the pack state of charge, and the pack voltage. So with a Veristand system, it basically is comprised of two things. What you see on the right is the system definition file, which allows us to choose a target. In this case, we're using a Windows operating system. We import our models in here, and any other communication to outside devices such as a BMS or the battery or Bloomy's battery simulator is all done here. The other half is the user interface, which you can see on the left here. Basically, this allows a user to control a test manually, enabling individual cells, changing the input voltage, changing the ambient temperature, changing the pack current, and all of this is mapped to the models, which then, in turn, create these outputs of voltage, state of charge, temperature, and internal resistance. So let me give you a quick demonstration now of what exactly it's going to do. So like I said before, you can run this manually. Another option that we like is using TestStand. We can automate these tests. So what this is actually going to do is automate the entire testing of a battery simulator or battery management system. So if I click this, basically, TestStand will initialize Veristand, open all the necessary project references, and run the configured project. It enters this loop where it's looking for whether or not the user started the test, and once it does that, it'll go into a real-time sequence. This real-time sequence is just a CSV file that is basically right now mimicking what a BMS, the signals that a BMS would produce. We don't actually have a BMS to use, so right now it's all simulated signals in terms of that are being mapped to the model. So running this will, like I said, launch Veristand, launch the UI that I showed you before, and load the system definition file onto the target, in this case, just a Windows operating system. And you can do this for a number of units under test, which is the UUT you see there. So if you wanted to test multiple ones in sequence with the same parameters and all that, this is actually probably the best way to do it using this software. So like I said, this is launching everything. It'll look for all of the hardware, initialize all of that. So the way that this test is set up is, like I said, we don't have the actual hardware, the BMS to control the software. So what we did was simulate everything, and there's a battery simulator hooked up in this demo, and the goal of that is to basically demonstrate all of the syncing and sourcing and the balancing currents, which is what you'll see right here. So these are actually being read off of the BMS at the moment, and the top 6 cells are actually sourcing current to individual loads. They're each wired to resistors, and these bottom currents right here are syncing from a power supply. So the first step, like you just saw, was enabling each cell, and then the user can actually start the test, and you'll start to see the pack current, the ambient temperature, and all that will change over time, and that's all coming from the real-time sequence CSV file. So the screen beforehand is nice in terms of being able to set things in manual mode and to see exactly what's happening instantaneously. But these graphs allow the user to actually see what's happening over time in terms of each individual cell and each parameter. So, and then you could also see the pack statistics, the pack voltage, pack state of charge, and temperature, all in regards to time and over the course of the test, as opposed to just the instantaneous that you get with the other screen. So basically, this is running at about 100 hertz, which means every second there's 100 different values going through this for each parameter. So it allows, like I said, it's running in real time, allows for very accurate results. And so right now, all of these cells are, right now the pack current is actually drawing from the, the pack current is positive, so it's actually drawing from the cells. So you'll see the cell voltages increasing, the cell state of charge is decreasing, and the pack state of charge decreasing. Pretty soon it should switch to, it will switch to a negative voltage, and you'll see the pack state of charge actually begin to increase instead, representing the cells charging as opposed to discharging. So like I said, these charts are nice to be able to see what we can, nice to see over time, and at the same time we can also map all of this to Veristand's embedded logger system, which will allow us to actually save all the data in a TDMS file, which can be viewed both in Veristand or exported to an Excel sheet where you can continue to post-process and analyze the data after a test is complete. So now we see pack temperature is still discharging, and then I jump ahead a little bit. Oh. So now pack temperature, the pack current has gone to negative, and now the pack state of charge should show that it's increasing as opposed to decreasing. So that's pretty much the extent of that demo. I'm going to turn it back over to Paul, and he's going to give a summary of the rest of the summary of this.
So what I'm going to do is share my and just wrap up really. So yeah, there's a lot of information being presented here, and well done everybody for making it very concise. So just really to wrap up, what we're offering here is a fully integrated open hardware-in-the-loop platform for rapid prototyping, testing of BMS control and monitoring strategies. This is all off-the-shelf industry standard platform, and is implementing our state-of-the-art physics-based cell models. We have many different cell chemistries available, flexible in terms of the cell stack configuration, and this is all done in the software. It's open, readily configurable in terms of the BMS I/O and fault insertion, and we see this as a very powerful and scalable platform in order to be able to get that level of fidelity that you need on the physics side in order to do much more realistic and valid testing of BMS systems. So with that, I'd like to thank you for your time and attention. We have actually we had some pretty good time here for if there's any questions.
Okay, we do have a few questions. I'm going to start, I think, with Steve and Ben. What happens when I release a new version of BMS? Do I need another system?
Hi, this is Stephen. Well, the entire intent of the design is to prevent that from being the case. So basically, this is a scalable platform in all senses. If a new BMS or a new version of your BMS needs to be implemented, you essentially have to reconfigure the Signal I/O to match what it is that you need. So essentially, take the existing capabilities of your system and remap those as appropriate in the software and in the hardware. The way you do it in software is by using the Veristan engine, and the way you do that in hardware is by creating another interface cable that goes out to your BMS. So it's really very controlled and bounded efforts that are required, but that same BMS platform that works for one of your BMSs should extend to many iterations going forward.
Awesome. Thanks for the question here. In the presentation, the HIL model was stated to run at 10 milliseconds. Can it go down faster, down to 1 millisecond? Some HIL tests require faster response to test out such as contractor control, etc.
That's probably one for you, Stephen. Yes, sorry, yeah, go ahead.
Yep, this is Stephen. I'll field that one as well. A lot of it depends on the content of the models themselves and how complex they are. We can certainly eke out a bit more performance on the on our side from the Maplesoft models, but if you're going to ultimately develop your own models and they're more complicated or processor intense, then we may need to evaluate it on a case-by-case basis depending on your specific model. So it's possible that it can perform better, or it's possible that we'd need to dial down the frequencies as well. So it would really need to be evaluated based on your models. But with standard off-the-shelf models from Maplesoft, we'd much more easily be able to extend that down to the 1 kilohertz.
Or 1 megahertz, yeah. Sorry, 1 kilohertz. You're right, yeah. Sorry, just to reiterate, certainly the models that we develop, they're highly optimized for HIL applications, and pretty much the standard execution time would be the 1 millisecond, 1 kilohertz frequencies.
I have a question here for Paul and Jonathan. If I have my own battery chemistry, can I bring this data into the battery model?
So I guess I can field that question. So yes, you can actually, and there's an option in our battery library that allows you to go and bring in your own half-cell model, and so that'd be your open circuit voltage as well as the enthalpy change for your chemistry that you're interested in. So you can definitely bring in your own experimental data.
Okay, I think this one would be for Steve and Ben. What are the next research steps or remaining practical challenges for physics-based models on HIL systems?
What are the next research steps? I mean, hopefully I'll answer it correctly. If not, please call back in or text back in. But with these models, really you're able to test your BMS in really an ideal environment based on those physics models. But as you begin testing your pack and seeing performance that differs and varies, I would say that the next step would be to adjust your models within the environment and have them better represent the specifics of your cell performance, and really go from there and retest and really validate the fact whether the responses correlate between those two different sets of models. So really the platform allows you to easily do that. You can swap in new models, make adjustments and retest and evaluate based on the logging and performance testing features how the response is executed.
I can probably just add a little more just in terms of where we see some of the research going in this area. One of the things that you probably notice about certainly the way that we implement these the physics models as they stand at the moment, they actually do need a certain amount of calibration, and this is specifically done from test data, so charge discharge data. So it actually does need a certain input from tests. One area that I can certainly see would be of great interest is, can we actually create a predictive model that comes from, say, a multiphysics model in a sort of FE type of application, take the information from the response information from that model, and implement that in a predictive model for HIL purposes. The way I see it is the path is already there to do it. It's just that I'm not aware of anybody's actually done it yet.
And what if I want to develop my own models? Can I still use the system?
100%. That's part of the open platform approach. You're not really tied in to the models that it comes with or the system specs that it delivers with. You can scale it, maintain it, and really, as you develop or move to different models, scale it as needed. And as you have changes to your BMS and to your firmware, continue those tests as well, and really scale it and use it really as an engineering tool to really facilitate your verification, your R&D efforts.
I'll even add to that comment too. That's a really good statement for both of our tools, whether it's the hardware that you're wanting to scale on or even the software you're wanting to scale on. Being able to go and create your own custom components and expand on that, as well as tap into any of the additional library features, you can definitely grow your model, change your model to meet your specific needs, and then exporting to Bloomy's platform, which is definitely reconfigurable to meet your needs. So in both systems, you can easily meet both of those requirements as your customized application requires.
Just to go a little step further with that, we should also point out that MapleSim is a multi-domain environment. So even things like being able to add in mechanical loads to electrical system, to actually come up with a way of representing dynamic loads on the battery, they can also be incorporated into the system model.
Okay, we have another question here. Actually, a comment. Great presentation. And then they're asking if an electronic copy will be shared or posted. I'll go ahead and answer that one. Absolutely. If you're a registrant of this webinar, any registrant of this webinar will be automatically emailed a copy of the recording when it becomes available, typically in about 2 to 3 business days. So you can expect that shortly. All right, I do have a question here. How scalable are the battery models? Is there a limit to the number of cells I can model?
I can take that one. Obviously, we're good, but we're not magicians. There are going to be computational limits to what you can actually do in terms of scaling these models up. Jonathan showed a pretty extensive benchmark that we did with 144 cells. That was for a large energy storage project, and we were able to handle that within the real-time budget of 1 millisecond. So it's we're pretty confident that you can actually scale this to some fairly significant networks. Once you start reaching the limits of your processor, then there may have to be some decisions made in terms of either parallelizing the grid or the battery system, or to simplify the model down.
Okay, I've got another one here, I think, for Bloomy. Do I need maintenance contracts if changes are needed?
Bloomy ships standard, our system's standard with 1-year warranties, but essentially it's not something that we typically expect to be needed. It is an open platform. I guess I'll say it again. So really, the product it's an engineering tool that our customers can scale, can maintain, and can upgrade as needed. Bloomy is certainly available and willing to help in terms of development on the platform, but typically it's not a needed feature within the offering.
Okay, well, I think we're at the end of our questions. Some great questions there, and really appreciate everybody's effort in this presentation, and certainly thank you everybody for attending and for your time and attention. If you'd like to find out more about this work, then you can contact us at info@maplesoft.com. With that, thanks for your time, and we'll shut it down. Have a great day. Goodbye.